Okay, let's get started. What I want to do today is to finish out the last little bit on phase diagrams and then move over to talk about the kinetics of changes in materials. In phase diagrams are maps which show equilibrium phases. In the simple case in which we're going to worry about them as a function of temperature and composition, we worry only about binary phase diagrams. What I want you to do is to know how to read any binary phase diagram and to understand a few simple binary phase diagrams, specifically the phase diagram for something that forms a solid solution at all temperatures and the phase diagram of a system that is a simple eutectic. We talked about those before. First, how do you read a phase diagram? To repeat, a phase diagram contains three pieces of information. Given a particular point, Tx, in the phase diagram, you can identify the phases that are present just from the phase field that point appears in. If it's in a single phase field, I have only one phase. If it's in a two-phase field, I have two phases. In this case, the point is in the two-phase field, so I have phases alpha and beta present at that temperature and composition. The second piece of information that's contained is the composition of the phases. If I'm in a single phase field, then of course the composition of the phase is the same as the composition of the solution. If my point were right here, my composition would be X alpha because that's the composition of the overall solution, and there's only one phase. If I'm in a two-phase field, then I determine the compositions by drawing a horizontal line through the image point of my system and determining the compositions from the intersections of that line with the boundaries of the two-phase field. If this is the point I'm interested in the two-phase alpha plus beta field, then the composition of the alpha phase is X alpha, where the tie line hits the alpha phase boundary. The composition of the beta phase is X beta, where the tie line hits the beta phase boundary. That gives me the compositions. The third piece of information are the fractions of the two phases. Well, now I know the overall composition of the solution, which is X in this case. I know the composition of the alpha phase, which is X alpha. Beta composition is X beta. Mass must be conserved, so the composition of alpha multiplied by its fraction plus the composition of beta multiplied by its fraction must equal the composition of the whole system. And if I just plug into that and the math is given in the notes, you get that the fraction of the alpha phase is X beta minus X over X beta minus X alpha. That is, the fraction of the alpha phase is the length of this lever from X to X beta over the length of the entire tie line. And F beta 1 minus F alpha is the length of this lever over the entire tie line. So that's the information that is contained in the binary phase diagram. Given T and X, you can determine the phases that are present, the compositions of those phases, and the fractions of those phases. Now let's look at the two kinds of phase diagrams I told you to try and understand, which we went over last time. Suppose we have a situation in which we have A and B, which form solid solutions at all compositions at low temperature. This should be alpha rather than A, and liquid solutions at all high temperatures. If that's true, at very high temperature, the liquid phase, I'll have a single free energy curve for the liquid phase, a single free energy curve for the solid phase. They will both be concave everywhere since these solutions are stable. At high temperature, the liquid curve will be everywhere below the solid curve so that the whole solution is liquid at all compositions. At low temperature, the solid curve will be everywhere below the liquid curve. So I'm in the alpha phase at all compositions. In between, the two curves pass through one another. And as you can see by the common tangent rule, what that is going to give you, in this case, is a lens-shaped two-phase region in which we have a mixture of liquid and alpha phases. So that's the kind of phase diagram you get for when we form solid solutions in all compositions. There could be a couple of alternate shapes. You can have a situation where this two-phase region kind of rises to a peak or sinks to a valley, but this is the simple one to remember. And we also discussed how you could use this kind of phase relation, for example, in zone melting or refining or purifying the composition of the material. The simple eutectic diagram, the eutectic diagram is the simplest phase diagram that you can have. When you have two solid phases, alpha and beta, that have different structures. Because if alpha and beta have different structures, I cannot simply morph alpha into beta. Therefore, I must have two independent free energy curves, one for the alpha phase and one for the beta phase. Therefore, at the lowest temperature, where these phases are dominant, I must have a situation like this, where I have alpha until I hit the common tangent to the beta curve, beta beyond x2, over here on the right-hand side of the diagram, and a two-phase region here at intermediate compositions. At higher temperature, of course, the liquid phase would intrude. It would cut that tie line between the alpha and beta free energy curve, that common tangent. And as a consequence, we have an intermediate region in which we have three phases in the phase diagram: alpha for A-rich solutions, beta for B-rich solutions, and a liquid field in intermediate compositions. Between liquid and alpha, I have alpha plus liquid. Between liquid and beta, I have beta plus liquid. And that gives me the simple eutectic diagram, which you've seen here and also seen in the laboratory. You did an example of the simple eutectic diagram, and it looks as shown here on the left. The simple eutectic diagram, one of the uses to which it can be put is to infer the kinds of microstructures you might get as you change the composition of the liquid and cool it down. And by picking your microstructure, by picking your composition correctly with respect to this diagram, you can generate several different microstructures. We briefly discussed what they were last time. In the simplest case, we consider microstructures X1, X2, and X3. X1 is a composition that passes directly through a two-phase region into a single-phase region, into alpha. So if a system with composition X1 solidifies, it will initially solidify, if it's at equilibrium, to 100% alpha phase. So we will have a polygranular body, presumably, that consists of the alpha phase. If we continue to cool the solution, however, we eventually drop out of this alpha region into a two-phase alpha plus beta region. When that happens, we'll begin to nucleate beta phase, which is very rich in B as a composition way over here. The beta particles will come out as discrete particles, maybe in the interior of the grains, maybe in the boundaries. That's a kinetic issue that we'll return to later, but leaving us with a microstructure something like this. And that's the common microstructure, for example, we'll see later, for precipitation-hardened material that we might use in some mechanical application. The other extreme is when we have a composition that passes precisely through the eutectic point. At the eutectic point, we get what's called the eutectic reaction. The liquid spontaneously transforms to a mixture of alpha and beta. This is just like freezing, because we go from liquid to solid. But now the solid is not one phase, it's two phases, alpha and beta. The structure that this thing tends to pick up, if we let it cool at some reasonably slow rate, is the classic eutectic microstructure, assuming we're out here at roughly 50-50 composition. And it looks like this. We wind up with a microstructure of grains, colonies, each one of which contains plates, generally, that alternate between the alpha and beta phases. And the reason for that microstructure is simple. When the liquid solidifies into alpha and beta, the compositions of the alpha and beta phases are dramatically different. So if I try to form alpha alone, I've got to dump a whole bunch of B into the environment, and that will impede the transformation. If I try to form beta alone, I dump a whole bunch of A into its environment, and that impedes the transformation. But if I let them come out together in such a way that I have essentially a planar interface that has the appropriate fractions of alpha and beta, then that interface can grow smoothly, because the alpha dumping B is picked up by the adjacent beta. The A dump from beta is picked up by the adjacent alpha. So the whole thing can grow as a unit. The intermediate case, which you saw in lab, if I come down at composition X2, I get into a two-phase region and begin to nucleate grains of alpha. However, before the solidification is complete, I hit the eutectic boundary, eutectic temperature. And at that temperature, remember the composition is, when I'm just at the eutectic temperature, the composition of the alpha phase is here at the alpha line, the composition of the liquid phase is right over here at the eutectic composition. So that material at the eutectic composition then promptly solidifies into eutectic material, and I wind up with a microstructure that looks like this, in which I have grains of what we call pro-eutectic alpha, and then a network of eutectic colonies, something like this. It's actually important for later to realize that it will be the low melting constituent, the eutectic phase, that will actually form the continuous network here. Here are just a couple of quick examples. Here are eutectic microstructures in tin bismuth and in indium-3 silver. In the tin bismuth, you have almost exactly a 50-50 composition, 60-43. So you see a well-developed eutectic, alternate plates. There's some jiggle in here because there are kinetic things that go on. So you very rarely get a perfect eutectic. In fact, there are certain applications where you would like to grow a perfect eutectic. I'll tell you about at least one of those later on in the course, and you go to great difficulty in order to do it. If you just let tin 43 bismuth solidify slowly, you get something that looks like this. And it's just a modification of that plate structure I was showing you. Yep. They're related to the diffusion and to the growth rate. The faster the growth rate, the thinner the plates are, as long as you keep the eutectic microstructure. There are actually, you can predict that. There's a well-developed theory of the growth of eutectics and the thickness of the plates that come out and so on. And it has to do with, well, there's a thermal issue, because when you solidify, you dump heat. There's a compositional issue, and there are diffusional questions, particularly how fast do these species diffuse through the liquid. You put all those things together, and you can crank and grind, and do a phase field simulation, and get a pretty good model of what's happening in eutectic growth. The problem you run into with any of these things are the uncontrollable features, the thermal noise of the system. Maybe you bump the container while these things are growing. You get something that looks like this as a consequence. Those are the things that are hard to model. As I said, there are a couple of applications where it would be really nice to grow a perfect eutectic. So it's not easy to do, and we'll talk about that later, of course. In tin 3 silver, you see again the eutectic structure. In this case, the indium is only 25%. So what you're seeing primarily here is silver, with a bit of indium. The bright things here are indium, and because because the fraction of the indium is much lower, these indium particles do not have the form of plates, but rather they form as rods. And that's why you see the structure you see. In many places you see sets of parallel rods growing here. That's indium, where you section along the rod. In many other places you see what look like discrete particles. Well, these aren't really discrete particles. What they are is you section through the rod, and you're seeing the rods more or less head on, and therefore they look like individual particles in this two-dimensional cross-section. For many purposes, you don't want this kind of eutectic microstructure. In eutectic solders, for example, many solders in microelectronics are eutectic phases, because in a solder you're always looking for a low melting point. And from the eutectic phase diagram, you see the lowest melting point you have is the eutectic composition. So solders tend to be eutectic compositions to get the melting point down, so solidification temperature down. And that will tend to give you eutectic microstructures, which for many purposes do not have very good mechanical properties. They're unstable microstructures. So you'd like to get more equiax microstructures in solids. And the way that you can do that is to dramatically increase the cooling rate. If you dramatically increase the cooling rate, this happens kind of automatically in many soldering operations in microelectronics, because your soldering bump is 50, 100 microns in size. And you just drop a 50-micron liquid onto a cold surface, it's going to solidify pretty quick. So you can get it naturally in many solders. What happens then is you get what's called a divorced eutectic. You just don't have time for that nice organized structure to form, so you get a very fine-grained intermixture of the two phases. And in cases where you're close to 50-50, tin lead 6337, tin bismuth 5743, you get an almost equal mixture of the two phases in a very fine-grained environment, which has a very, very good set of mechanical properties in things like solder contacts. So this lead tin eutectic, which has a low melting point, it's relatively inexpensive, has a very good microstructure, would cool quickly, was the great white rat of the entire electronics industry until people decided they didn't like lead anymore and caused something of a revolution. Revolution has produced something of a problem, because what we've gone to in lead-free solders is silver tin or silver copper tin, silver copper. All of these systems have a very off-symmetric eutectic. In the case of tin silver, it's way over here, just about 3% silver. This leads to a microstructure which is not as pretty as the ones you saw before. It's a microstructure which is primarily tin with just a little bit of silver, which comes out, this is actually 4 silver, 0.5 copper. That's a ternary eutectic. You get silver 3 tin islands, a distribution of them in what look like the grain boundaries of the tin, or sometimes they appear as very long needles. Neither of these microstructures is particularly attractive for mechanical purposes. An awful lot of what's happening right now in this particular technology, which is a huge field actually, is getting the grain sizes of the tin down and controlling these microstructures. Silver is becoming increasingly unpopular. The other one to finish up on is what's called a eutectoid. This is perhaps the most important phase diagram in the history of technology. This is the iron-carbon phase diagram, which is the basis of structural steel. In iron-carbon, you have a low-temperature BCC alpha phase, in which the equilibrium solubility of carbon is so low that it hardly doesn't even look like a phase field over here along the boundary, but it is. At higher temperature, you have the FCC gamma phase, which has much greater solubility of carbon and provides this field right here. Now, first of all, if you go up to the liquid, you'll see here a nice eutectic. In fact, two different eutectics, depending on whether you're talking about forming gamma plus carbon, which is actually the equilibrium situation, or gamma plus carbide, Fe3C, which for kinetic reasons is what you usually get when you cast iron. You have a eutectic right here that's familiar. Here's exactly the same thing, but now we have the reaction gamma FCC going to alpha plus carbide, alpha plus Fe3C on cooling. Because both of these phases are solid, this is called a eutectoid point rather than a eutectic point. I didn't do that. Somebody else did it. There's absolutely no difference between a eutectic and a eutectoid, except in one case we have a liquid going to a solid, in the other case we have a solid going to two other solids. But anyway, this is the situation in iron-carbon. This, incidentally, gives you one indication of all of the things that you can do to control steel. I come up here in the gamma phase, I can control the carbon content. Controlling the carbon content, when I cool down, I can trap carbon in the alpha by cooling very quickly. I can cool more slowly and let the carbon come out in various ways. So this gamma to alpha phase transformation in iron is really the basis of the processing of structural steels, because it allows us to control what happens. We'll talk about this later when the transformation occurs. Yeah.
So if you're controlling the carbon, you're cooling the steel, how do you remove the carbon?
Well, if I'm up here and I cool slowly, the carbon will come out naturally in the form of carbide. So I'll end up with an alpha phase that has carbide precipitates in it, or I'll end up with a pseudo-eutectic looking thing that we call pearlite. You haven't done the steel lab yet, have you? You'll see this. You'll see that in the steel lab. If I get that carbon in and cool it very quickly, then I can trap the carbon in the lattice. and I can render this gamma unstable with respect to a spontaneous transformation, which traps carbon in the lattice and produces the very, very hard steel called martensite, called a martensitic transformation. We'll talk about it a bit later. But the possibility of cooling slowly and getting gamma plus ferrite, ferrite plus alpha, by itself is called ferrite, ferrite plus carbide, or cooling very quickly and getting martensite, is the basis of the control of the structural properties of steel, which is how you can go from a yield strength of about 20 KSI, 1,000 pounds per square inch, up to almost 500, depending what you do. Enormous variation in properties that you can control just by how you heat treat the alloy in this region and let the transformation happen. We'll talk about that a little later. Okay, that finishes what I want to say about phase diagrams, and that brings us to the second thing we've got to understand to see how microstructure is controlled, how materials respond to thermal and chemical changes, and that's kinetics. Remember, to understand what a material does, we've got to know what it wants to do. That's the thermodynamics. It's not going to do anything thermodynamics as it doesn't want to do. But the fact that it wants to do something does not mean that it can. So the other thing we have to understand is the kinetics. What can it do and how fast can it do that? And in fact, virtually all of the processing of materials involves a rather simple thing, really. You bring the material into a situation in which it wants to change, in which there's a thermodynamic driving force for it to change. You let it start changing. You choose kinetics. You use kinetics to control the path by which it changes and how fast it evolves along that path. And then when you get it into the situation you want it, you quench it or otherwise use the kinetics to bring the transformation to a halt. Virtually all materials that are used in engineering are trapped in metastable states to achieve the microstructures and properties you want. And they are intentionally trapped there. And the whole art of processing is using the thermodynamics to force the material into some evolution, using the kinetics to control that evolution, and eventually to bring it to a stop where you want it to quit. And we'll see examples of that all the way through now. I'm sorry? Sometimes not. This is exactly what transformation I'm talking about. Most microstructural changes, they can be reversed in the sense that you can erase them and start all over again. But transformation paths are very, very rarely directly reversible. Usually, if you want to get back where you started, you got to erase the microstructure and begin from the beginning. Okay. Well, I'm going to say there are two kinds of kinetics that we need to be concerned about. First of all, they're continuous transformations. The classic example are the diffusion of heat, the diffusion of mass. We violate the conditions of thermal and mechanical equilibrium, and things just begin to change slowly to get back into equilibrium again. You touch a hot skillet, your finger and the skillet start coming to thermal equilibrium, and you can quickly feel that this change is taking place. If you, those are continuous changes, and we'll discuss the diffusion of heat and mass. The other thing that can happen are discontinuous changes, mainly structural phase transformations. I just talked about one. You take iron, phase center cubic gamma phase at high temperature, you cool it, and it undergoes a structural transformation. That's a discontinuous change to wind up in the BCC alpha phase with perhaps some carbon. So let's talk about these. The continuous changes are driven by deviations from local equilibrium. Remember, our conditions of local equilibrium, the temperature's got to be constant, pressure's got to be constant, chemical potential's got to be constant. The two we'll talk about here, because we're not on mechanical properties yet, have to do with heat flow in response to temperature gradients. If the temperature is not constant, heat will flow from hot areas to cold areas to bring it back into equilibrium. Or the diffusion of mass, atoms, in response to chemical potential gradients. Well, we ordinarily develop a chemical potential gradient just by putting in a composition gradient. So we tend to think of diffusion of mass flow as resulting from gradients in the composition. It isn't really a composition gradient. It's a gradient in the chemical potential. And while it's beyond the scope of this course, I can easily describe to you situations in which diffusion will spontaneously occur up a concentration gradient because something has made the chemical potential go the other direction. But ordinarily, a chemical potential gradient and composition gradient are the same. The deviations from global equilibrium are given by the overall potential, the change in the Gibbs of the Helmholtz freedom. The first thing we can talk about is the flow of heat. Let us have two regions of a bar here. We'll do a one-dimensional problem in which there is a gradient. This region, T2, is greater than T1. As a consequence of that, we're going to get a flow of heat, energy in the form of heat, from the hot region to the cold region. And we can define that as a heat flux. That is, the heat that flows from T2 to T1 will be a given transfer of energy per unit area of the surface divided. And that's what we call a heat flux, the heat flow per unit area per unit time. From the second law of thermodynamics, you can easily derive Fourier's law of heat conduction. You've seen it before, I'm pretty sure. I'll just write it down. That the heat flow is equal to minus K, where K is the thermal conductivity, times the temperature gradient, dt dx. This is the driving force, the temperature gradient. This is the response, the heat flux, and this is a constant of proportionality. Why does the law have this form? It has this form for a very simple reason. Most of what you call the laws of physics are, in fact, nothing more than Taylor expansions. Suppose I say, if I have a temperature gradient, I'm going to flow of heat. I mean, that's just a statement of the second law. We know that. How can I describe that flow of heat? Well, I can describe that flow of heat in terms of a Taylor expansion, in which I just let it be a zero term plus a term proportional to the first gradient plus a term proportional to the gradient squared and the second gradient and so on. The lead term in that Taylor expansion will look like this, because when the temperature gradient goes away, the heat flow goes away. Well, that's a digression of sorts, because in most books you see this stated as a law of physics. But most of the quote laws of physics are Taylor expansions. This is just, what must happen is there must be a heat flow. The lead term in the expansion for the heat flow is this, and that's called Fourier's law of heat conduction. The material property here is the thermal conductivity K. So that's the thing we've got to understand how heat is conducted in materials. In addition to the heat conduction, well, actually what we really care about is not the flow of heat. In fact, it's enormously difficult to come up with an experiment that would measure a flow of heat all by itself. What we really care about is the change in temperature.